Okay, thank you very much, Romain, for the presentation and also for the invitation. It's a pleasure to give this colloquium. So it's one of the good opportunities that we have now during these times that, I mean, we have to work from home, but these opportunities to do this kind of virtual meetings is also like opening frontiers for science. So it's nice to be able to help keeping running the science. So I'm happy to give this talk. And as Romain mentioned, I want to, I'm working we have a nuclear magnetic resonance lab. So I will try to, the idea is to try to show you how we can develop techniques from quantum physics and quantum information processing, mainly to study the dynamic of what is called quantum information, the dynamic of quantum systems, that they are called systems that are out of equilibrium. And I will show you some techniques how we can study this propagation of information in quantum systems. And in particular, I hope that at the end, I want also to show how with these techniques we can study some kind of physics, and I will show you what I mean with this, the coherent scaling transition in the dynamic of quantum information scrambling. So just a bit to give you an idea, what is the main motivation that we are pursuing in our research is related with the huge project, that the progress that was being developed during the last time, that we are able now to, we have a lot of control how to observe and how to control quantum systems. There was a lot of progress on doing that. In particular, we are now able to control individual quantum systems that like photons or electron or nuclei. And this is now leading to what is called the developing of quantum technology. So there is a lot of interest in several countries that are like the flagship innovation and research lines that several countries are pushing, is to try to develop these quantum technologies. And the point is of these quantum technologies is to use quantum system to develop devices. And this, I mean, this area of research and development arise because in some moment we realize that, I mean, we are all the time improving our computers. And if we want to continue improving our computers, what we do is to make the circuits smaller and smaller. And very soon we will need to, if we want to continue with this direction, we will need to control a quantum system, and we will need to be able to process the information to do computation using quantum systems. But the problem is that the law of physics are very different when we are time and we need to control atoms, because now the rules are dictated by quantum mechanics and not by classical mechanics. So this is what they started the field that is called quantum information processing, to try to use how we can use these quantum systems to store and process information. So this is one of the things that there was a lot of work trying to develop this kind of techniques to create computers using quantum systems. This is what is called quantum computation. Where the idea is that instead of using classical bits where you have a 0 and 1, we can use, for example, two levels of a quantum system that can be a spin 1/2, where we have the spin up and a spin down, as I'm showing in this plot. And we can store the information in quantum level of the system. And these have a lot of properties that can produce in several situations computation that are much faster than with the classical computers. But this is a very challenging project. At the moment, we need some time still to be able to create universal computers. But what is interesting that we trying to build these computers, we learn a lot how to control quantum system, and this is what is allowing us now to use these techniques to develop different devices for a specific task. So there are different targets to develop these quantum devices. I will focus now in two of them mainly, that are the lines that we are pursuing, and also is more or less related with the tricks that I will mention, is that we can use, for example, we don't need a universal quantum computer, for example, to simulate complex systems. If we want to simulate a very large quantum system with a classical computer, it's very difficult because sometimes we don't have enough memory to store the information, or the calculation is very slow. But if we are able to control a quantum system to mimic and to reproduce what will happen with another system that we cannot study, this is what it's called quantum simulation, and we can use a quantum system to simulate another complex system. And with that, we can be able to calculate or to study system that we cannot calculate with classical computer. So this is one of the devices, that is devices that are prepared to simulate some complex systems. And the other interesting thing is that also we can use quantum system as sensors, and we can probe matter or fields at atomic scales. So there are a lot of interest also to use these quantum properties to develop this line of tensor that have a lot of application, for example, in biology or medicine. And the idea that there are very similar papers where we are showing that we can use an individual quantum system. For example, one of the, here is a plot of a diamond. The people is using diamonds with some impurities where they have a single spin, and this single spin can be coupled to molecules. And for example, we can study single molecules or single atoms or single nuclei. And we can detect information for very small scales. We can put this diamond inside cells, and we can study the physics inside the cells and have a lot of promising applications. But one of the challenges is that the quantum system, the quantum properties are very sensitive to external perturbations. So, and not only with external perturbation, but sometimes also when we want to control a quantum system, also we distort the quantum system, and sometimes the control also is not perfect. So all this external perturbation and combination of imperfect control, what does is to destroy the quantum information and the quantum properties of the system. This is something that is called, this loss of quantum information is called the decoherence, and what happens is that these quantum features disappear very rapidly as a function of time. And this is one of the challenges that a lot of people is trying to develop techniques to protect this quantum information so we can do these quantum devices. There is a lot of progress to be able to control few body problems where the quantum system is very small, but it's very difficult, and it's a huge challenge to be able to control very large quantum systems. So if we have very large quantum systems, the quantum superposition between all the elements of the system are very complex and very sensitive to this external perturbation. As larger is the system, it's more sensitive to the perturbation, so it's more difficult to protect this, what is called many-body quantum system. And it's not easy to adapt the techniques that were developed to control individual quantum system or few-body system, adapted directly to many-body system, because the degrees of freedom that they have a many-body system is much larger than the other, and it's not trivial how to expand these techniques. So this is a huge challenge, how we can be able to control in a reliable way the many-body quantum system. So this is one of the main motivations, what I want to try to use quantum simulators to try to study how is the behavior of many-body quantum system and how is the behavior of the dynamic of this many-body quantum system to be able to control them in a really reliable way. So, and in order to try to understand this problem, what I will try to do is to try to answer a very simple question, and I will try to focus in this talk to show you how we can try to answer this question. And the point is that if I want to control a quantum system, what I will use is a Hamiltonian to process the information, or to store the information will be controlled with some kind of Hamiltonian. And this is what I will call the H0 Hamiltonian. This is the Hamiltonian that I want to use to control the information. But always, as I tell you before, there are perturbation or external perturbation that I'm not able to control. And this is what I call sigma. And this will be a perturbation that I will have in the Hamiltonian. So when I want to try to control the Hamiltonian, I will intend to apply this Hamiltonian, but I will have a perturbation. So the question I want to answer is how does this perturbation will modify the processing of information, or will modify the dynamic of the quantum system. And Of course, it's a very simple question, and there are different ways to answer it. So what I will do is to try to show you some kind of paradigmatic experiment and paradigmatic system where what we will do is to use a spin system. As I told you before, I'm working in nuclear magnetic resonance, so what we can do is to look at nuclear spins, in particular 1/2 spins. We are able to create some kind of local, sorry?
Gonzalo, sorry, you have this small banner, meetgoogle.com is sharing your screen. If you can, we can actually see it. If you can slide it on the, you can slide it completely.
This?
Or hide. Ah, no, sorry. Yes, okay, perfect. Thanks. It was, thank you.
Okay, sorry. So now you see completely.
Yes.
Okay, so this paradigmatic experiment that we use to answer this question will be that we can do experiments where we can create some kind of local information. This is what is shown here with this red spin. And what we will do is to, with this H0 Hamiltonian, is to control the dynamic evolution, to propagate this information into a cluster, what I will call a cluster of correlated spin that I will call K. And there will be some kind of, I will create quantum superposition between several spins where the information will be propagated by this H0 Hamiltonian. And what I want to try to study is how this information can be propagated to the network, but in a controlled way. And I want to try to understand how many spins I can propagate this information in a controlled way. Okay? This problem is very similar. For example, if we imagine a glass of water and we put a drop of tint, we will see that this drop of tint is at the beginning is localized, so it's some kind of this local information. And then because of the diffusion process, there are a Brownian motion, this drop of tint will start to propagate in what is called the network, in this case will be the water. We will see how this information is propagated into the water. But there is a difference, that here, the propagation of the tint is in a random way, and I'm not doing that in a controlled way. So if I want to use this information, it will be very difficult because I'm not able to control this propagation of the tint. So what I want to do is to do this, but in a controlled way, and I want to try to assess how well I can do this propagation of information in a network, okay? And because we are interested to work with very large system, we are able to do experiment with about 10,000 spins. So it's a very huge quantum system, and this is impossible to do it with classical computer. With classical computer, we can work with about 25 spins or something like this, but with the experiment, we can go to 1,000 of spins. So I will do what is called quantum simulations, and I will use NMR experiment to perform this quantum simulation of this paradigmatic experiment that I'm showing you with this slide. Okay, so this is the question I want to answer. So now I want to show you some tools that I will need to try to quantify how is the propagation of information and try to quantify how well this information is being propagated. So what we will do is to start from an initial state that is the information is local. So this will be a density matrix that will be related with a local magnetization. Then we will apply the Hamiltonian. If the Hamiltonian is ideal, they will be only the H0 Hamiltonian. So what will happen is that this state will evolve in time. So this is the evolution operator. I said are spin operators. And what will happen is that we will see that the evolution of the initial state will be the evolution of this I said operator. And this note here is representing that the evolution is ideal, and I'm doing that with the control Hamiltonian. So the way to propagate information, how the information is propagated, will be stored in the density matrix of the system. However, if I have a perturbation, now the evolution will happen again. I will create quantum superposition due to the evolution between several spins, but now the evolution will be detected by the evolution operator of the total Hamiltonian that include the perturbation. So I will be able to propagate information and to connect the spins, but not in a controlled way. And what is the point and what is more important is that this propagation of information will not be the same than the one that I will achieve with the ideal control Hamiltonian. Okay, so this is the main difference. If I have a perturbation, the propagation of information will be different than the one that I will produce with the control Hamiltonian. And if I want to use this information, I have to be able to do it in a controlled way. So what I want to now to do is to try to see how well I control the information. I want to compare these two dynamics evolution and see how different they are. And for that, I will show you how we can introduce some kind of fidelity that we will compare with some kind of inner product operation. We will compare the density matrix of the perturbed evolution with the density matrix of the ideal evolution. And this will be equivalent to study what is the evolution of this initial local excitation. This is what is represented here in a perturbed situation or an ideal situation. And this will give me some information about how well I was able to process or propagate this information.
Just a question. This rho zero is the current part of the pseudo pure state, right?
Exactly. Yes.
Oh, okay. Thank you.
Yes. So yes, I didn't mention the detail, but in NMR they are some kind of pseudo pure state or something like this. It will be something equivalent to that. Okay.
Okay. Thank you.
So this is the idea how I will do the things. So now I will show you exactly how, more or less exactly how we do that in the experiments. So what we do in NMR is to put this sample that, well, in our case is this sample is called adamantine. We will look at the hydrogen spins, and with that we will have a network or a spin-spin network where the spin are interacting with dipolar interaction. Initially, when the magnetic field is very strong in NMR, so the initial state will be like the total magnetization will be aligned with the magnetic field. And this is a sum of all the individual spin operator in the z direction. So it's a macroscopic magnetization, but it's an ensemble of local excitation. So what I will study will be an ensemble, evolution of an ensemble of local excitation. So essentially what I will be doing is this will be what represent this local excitation, and then I will see how this local excitation will be propagated into the network. The raw Hamiltonian of the system is the dipolar interaction, and because the Hamiltonian is very strong, the dipolar interaction commute with the magnetic field, and what happens is that commute with this initial state. So this raw interaction doesn't create correlation between the spins, because conserve the total magnetization number that is called MZ. So what I will do to create this propagation of information is to quench the system and to create a different Hamiltonian that is not the raw Hamiltonian. For that, I will not enter into detail, but there are some techniques that are called engineering Hamiltonian or average Hamiltonian theory, where we can manipulate the quantum system, in our case with the electromagnetic pulses. We can manipulate this quantum system to create an effective interaction between the spins. And so for the point of this talk, what I will do with these tricks is to create this Hamiltonian, that this is what I will call the H0 Hamiltonian. And in NMR, this is called a double quantum Hamiltonian, because if you see the spin operator are the plus plus and the minus minus. So what does this Hamiltonian, if I have two spin up, and the way to generate the interaction is to flip two spin at the same time. So this Hamiltonian, what does is doesn't conserve the total magnetization number, so doesn't commute with the initial state that is this local state, and will start to flip two spins at the same time, and with that we'll start to create quantum superposition. That is what I'm represented with this plot in the right. So this Hamiltonian will start to propagate this information, creating quantum superpositions, and I will be interested to see what is the extent of this propagation of information. There will be some kind of coherent length, how the information was propagated, and this will define a cluster size of correlated spins. And to answer the question that I told you at the beginning, what I will do is to use this double quantum Hamiltonian that propagate information as the ideal Hamiltonian. This is the H0 Hamiltonian. Then I will be able to control this perturbation strength also with this tricks of electromagnetic pulses, I will be able to control the perturbation strength, that is this P, and the perturbation will be the raw Hamiltonian. So this Hamiltonian doesn't commute with the initial state, this propagate information. This Hamiltonian commute with the initial state, so doesn't propagate information. So in some sense, it will start to affect the propagation of information. I want to try to assess how this perturbation will start to affect this propagation of information. Okay, so this is how we will set the problem. And now I will tell you a bit how we can measure how this information was propagated in a network. And for that, we will use some kind of technique that are called multiple quantum coherence. This is a term that was developed in nuclear magnetic resonance. That essentially what we do is to do a tomography of the density matrix. But it's a partial tomography because we will not be able to see all the elements of the density matrix, because if the system is too high, the element of the density matrix increase exponentially with the system size, so it's impossible to measure all the elements of the density matrix. So what we'll do is to measure some specific element of the density matrix that will tell you information about how many spins were correlated by this propagation of information. So this block here is a representation of the density matrix. Is in order, and I'm using the Zeeman basis, that are all the possible combination of a spin up and down, and they are ordered as a function of the magnetization number, that is the difference between the spin up minus the different spin down. This is the MZ magnetization. So here, for example, I have a block where the difference between a spin up and down is 0. I have all the possible combination that give me a 0 number. Here I have a 1, here a 2, a 3, and etc. So in the diagonal, I have the populations, and the initial state will be diagonal in this density matrix representation. Then the H0 Hamiltonian, what does is to connect Zeeman state that differ by 2. As I told you before, this is the solid lines. Connect a state that differ by 2, and the perturbation only connect a state that conserve the total magnetization number. So if I have an evolution, I start to evolve, what happens is that this state will start to be connected with this state will be connected with this, and what happens that in the density matrix they start to appear coherence of the density matrix, that they are the non-diagonal term of the density matrix. So if I connect these two states, the -1 and the 1, what happens is that I will create a coherence in this block here. And this is what is called a double quantum coherence, because connect a state that differ by 2. So here the different gray colors are defining what is called the multiple quantum coherence and the quantum coherent order. If I connect two states that differ by 2, is a double quantum coherence. If I connect a state that differ by 1, is a single quantum coherence. If I connect a state that differ by 3, is a 3 quantum coherent, and etc. So as far as I'm from the diagonal, the order of the coherent number is increasing. So what will happen when I start to evolve is that this coherent will start to be populated, and at the beginning, for example, these two states will be correlated, but then this state can be correlated with this. So also this state will be correlated with this and will populate a higher coherent order. So what will happen is that at the beginning, now if I do some kind of histogram measuring how these coherence order are populated or are excited, I sum all the same coherent numbers, so that means I sum all these blocks for different colors, and I will do some kind of histogram how these coherents are being populated. And what we will see is that at the beginning, only the 0 quantum coherent, because the density matrix at the beginning is diagonal, only the 0 quantum coherent will be populated, is only this element. But as the time passes, what will happen is that higher order of coherent will start to be populated. And what happens is that the width of this distribution will start to increase as a function of time, telling us information about how this information is propagated in the network. So this is what we will do. What we will do is to try to see this multiple quantum coherent element of the density matrix. And to do that, what we will do is, because we cannot do that directly, so we use a trick that what we do is to create this, we propagate this information. What we'll do is to apply a rotation around the set number. So when I apply a rotation to the density matrix, what will happen is that the density matrix will be decomposed in the different coherent orders. So here is all the elements of the density matrix. They have a same coherent order number. This is what I will call delta M. And when I apply this rotation, they will acquire a phase that is proportional to delta M. And this will allow me to distinguish the different coherent order of the density matrix.
So, Gonzalo, just a quick question. So with this representation, are you able to say anything about multipartite entanglement, or you can only say that, okay, it's a coherence that you're building up, but you don't know the nature?
Yes, so it's a good question. It's a tricky question also, and I will show you later that there are some new very recent paper that they show that actually this is a witness of entanglement. The only problem is that in my case that I'm working, if I'm working with pure state, it's very easy. This is witnesses entanglement, so you can be sure that there are some ways to say if you have entanglement or you don't have entanglement. In our case, we are working in a high temperature limit. So as someone asked before, we are working with some kind of pseudo-pure states. So if we look at the pseudo-pure state, maybe we have entanglement. But if we see at the full density matrix, there are no at the moment measures that can, there are some measures that say that there are not entanglement, because we are seeing an ensemble of several entanglement, but when you see the average, it's very difficult to quantify if you have entanglement or not. But but this is still an open question, how to define entanglement in a very high quantum system. So in some sense, the quantum superposition, for sure there are entanglement, but we have an ensemble of a lot of entangled states that when you see it macroscopically, it's very difficult to quantify the degree of entanglement. So the problem is we don't have a metric to do that, and it's not, I don't think there are a unique answer if we can call this entanglement or not, because we are in this high temperature limit.
I see, okay, thank you. But
for pure state, yes. Okay, so this is what we will do. So how we can measure now that, I will do this technique to encode the different coherent order of the density matrix, and now I want to measure them. So to measure them, I will do another trick that is called time reversal echo, so it's also called a many-body Loschmidt echo, and I will use that also to measure what I tell you at the beginning, what is the fidelity. I cannot also measure directly the fidelity, so what we will do is to apply these time reversal echoes to measure this fidelity. In NMR, or typically in several other situations, what we can see is the magnetization of the system. So this is this I Z operator. So what we will do is to start from the initial state. This is this local information. We will apply something that we call a forward evolution with the H0 Hamiltonian. This is my ideal Hamiltonian. Then I will apply this rotation to encode the coherent order of the density matrix. And then I will change the sign of the Hamiltonian and go backward in time. I will evolve the dynamic backward in time, and then I will detect the magnetization. So this is what I will detect, the magnetization as a function of time of the density matrix that evolved the forward, the rotation, and the backward evolution. And what we can see, if we reorder then this old evolution operator that appear here, that this is equivalent to measure a fidelity that is the inner product that compare the density matrix that evolved in the forward evolution and then was rotated, and I can compare it with evolution with this backward evolution that this is rho of t. So this gives me this fidelity, and if I apply the rotation, what will happen is that the different element of the different coherent order of the density matrix will acquire this phase proportional to delta M. So I will be able to look at the element of the density matrix with different coherent orders because they will achieve a different phase. And this is the trick that I will use to measure the element of the density matrix that have a different coherent order using this trick of time reversal echoes. So if I measure now the signal, I will detect as a function, I evolve forward, I rotate, and then go backward in time. If I measure the signal as a function of the phase, I will see something like this. When the phase is 0, I go forward with H0 Hamiltonian, then I go backward with the ideal Hamiltonian, so I will revert completely the evolution, and I will have what is called a perfect echo. This is the maximum signal. However, if I start to rotate, here I will propagate information in several spins. I will mix it with the rotation, so the quantum superposition will acquire different phases. So then when I want to go backward in time, the state was not the same, and I will not be able to refocus the information into the local state. So what we'll see is that the detection here will start to decay as a function of the rotation phase, because the information is scrambled and I cannot recover it. So this is what we'll see. For example, if we have a pi/2 phase, I mix it completely the state. Then if we have a phase p or 2 pi, I will not affect I will be able to refocus the evolution, and we'll have again a perfect echo. So now this signal as a function of phi is proportional to this. So if I do a Fourier transform of this, I will get the distribution of the element of the density matrix, and I will obtain the histogram that I showed you in the previous slide. So here all these points are experimental measurement of this partial state tomography, where I'm showing you the histogram of the element of the density matrix. And as I told you before, as the time passes, the propagation start to propagate in more and more and more spins, and what happens is that the width of this distribution start to increase as a function of time, and this also was developed within NMR, that if we measure the width of this distribution, we can have information about how many spins were correlated by the quantum evolution, and this will give me the cluster size that we'll call K, the cluster size of correlated spins.
I have a question. The minus signal in backward Hamiltonians, you can control that using I forget the name, but the point is,
so they are pulse sequences. So I can manipulate with the pulses. We can rotate the spins, and by rotating these spins, you can change effectively the sign of the Hamiltonian.
Okay.
So imagine, imagine that you are in the Earth. We have the gravity pointing down. If I'm rotated, now the gravity will be pointing up. So this is the trick that we do in NMR to change the sign of the Hamiltonian. You see?
Yep. Yeah, but my question is about what's the parameter we are changing in order to put this. Is the frequency of the radio frequency field?
To change the sign?
Yeah.
No, it's some kind of rotations. So what we do is to rotate the spins, so the direction of the interaction is changed because we rotate the spin and see the interaction in a different direction. So it's more or less like this.
Okay, I understand. Is exactly, for example, you rotate the sample of the spins, right?
Not the sample. What we do is to rotate. So the nuclear spin have a spin state, and this spin state can be up or down.
Mm-hmm.
When you apply a radio frequency pulse, what you do is to rotate the magnetization.
Okay.
So it's not like you rotate the sample mechanically. What you rotate are the quantum states that are in the nuclear spin. And by doing these rotations, it's a bit more complicated what I tell you, but essentially what you do, when you do this kind of rotations, you can change the signs of the interactions, and it's not only one rotation. There are several rotations when you apply all this operation, or you can see that effectively the sign of the Hamiltonian is changing.
Okay, yeah. So in this case, it's a pi pulse in the system.
It's a sequence of pi/2 pulses on different axes.
Okay, thank you.
You're welcome. Okay, so this is the trick how we can measure the multiple quantum coherence. And also, as I tell you before, I want to see the fidelity between the perturbed evolution, this is the H Hamiltonian, this includes the perturbation, and I want to see the fidelity with the evolution of the H0 Hamiltonian, of the ideal Hamiltonian. So then what we do is to modify the experiment, evolve forward in time with the perturbed evolution, we rotate, and then we go backward in time with the ideal Hamiltonian. So now what will happen is that now the fidelity will compare the ideal evolution, this is the density matrix of the ideal evolution, with the perturbed evolution. And if I apply the rotation, now what I will be able is to not only to compare the full density matrix, but also I will be able to compare the blocks of density matrix that have a same coherent order, and I will be able to compare these blocks depending on the coherent order. So I can do I can measure the full fidelity, but also I can measure how is the fidelity, the contribution to the fidelity for the different coherent order of the density matrix. So then, if I apply this perturbation, before we have the black squares, when I apply the perturbation, we will see that the signal is attenuated. If I have a rotation that is 0, because the forward evolution is different to the backward, as I told you before, the propagation of the information here is different to the propagation of the information here. So when I compare them, I will see a decay of the fidelity, and that means that I cannot revert completely the time evolution. So even for a 0 rotation, we will see a decay of the signal. But then if I do a rotation, I will be able to not only measure the fidelity is here for phi equal to 0, but if I apply the rotation, I will be able to look at the fidelity for the different coherent order of the density matrix. And if I do a Fourier transform, what I will get now is the effective number of correlated spins that were correlated in a control way. So this number of correlated spins will tell me how many spins were correlated with the ideal evolution, what survived the perturbation. So here I know that before I was able to control some number. With this, I will control maybe the same number when I compare the two propagation of information, the phases will be different, and the effective number of correlated spin that was controlled in the same way of the H0 Hamiltonian will be smaller, and I will get what is the number of the effective number that was controlled by the ideal evolution.
So,
okay?
Gonzalo, just a quick question again. So what happens exactly for pi over 2 here? What sort of state are you reaching? Because you always, independently of the perturbation, you go to a 0 fidelity, right? For pi over 2, independently of p.
The point is that because the phase that you acquire there, because you have all the coherent number in the density matrix, when you apply these rotations, they start to, it's like they are fully dephased. And then they interfere destructively, and you cannot see a signal.
Okay.
Essentially, this is the point. When you have this pi over 2, you have a destructive interference. So it's like, essentially, it's like all these magnetization are pointing randomly in several directions, and you cannot see it.
Okay. Thank you.
Okay, so this is the tricks, and this is the last trick that I will want to tell you that is related also with the question that you asked, Romain. Very recently, in 2017, Ana Maria Reid realized that she was able to use these tricks that I told you before, multiple quantum coherence, how to study the dynamic of quantum information propagation in a spin network, and she discovered that she can use these techniques to connect it with something that is called quantum information scrambling. And they are related to something that is called out-of-time order correlations. So I will tell you a bit what is this. Essentially, this paper, and concerning your question, Romain, this second paper is where they show that we can use this multiple quantum coherent experiment, as I showed you before, as a witness of entanglement. Is this a physical review letter of 2018? So the point is that this experiment that I told you before, that I go forward in time, I apply a rotation, and then backward in time. Now, if we rewrite what is inside of this trace, we will see that we can create this product of operators that, if you look at this is an operator that is evaluated at time 0. This is an operator that is evaluated at time t, then at time 0, and then at time t. And this is what is called an out-of-time order correlation, because typically the most classical correlation is that you correlate an operator at a given time and then look at this operator at a following time. But here, you are correlating operators that are not ordered in time. So here is a larger time, then is a lower time, and then is a larger time. And this is what is called out-of-time order correlations. And the point is that this complex correlator give information of what is called information scrambling. What is the information scrambling? Is the experiment that I was telling you before. If I have a local excitation, I propagate this information into the network. This information is what is called a scrambling into the network. And once it's a scramble and it's propagating into the network, I was not be able to access to this information from a local measurement. And this is what is called a scrambling. All this information that was initially in a point is mixed, so it's a scrambling into the system, and then I cannot recover it anymore from a local measurement. And in some sense, so it's giving information how the information is propagating in the system. But what is more important, and this is what is more interesting for us, is that this out-of-time order correlation, you can see that the cluster size is something that we see, that the cluster size of correlated spin that we were measuring with this multiple quantum coherence is proportional to, this is a bit more complex out-of-time order correlation, that is an inner product between the commutator, between the local initial state and the evolved state. So this commutator is telling you what is the degree of non-commutation between the evolved information with the initial state. If as larger is this non-commutation, the information is more scrambling and more scrambling into the system, and this is related with the number of spins where the information was propagated. So all this paper here that I'm showing there, I started to use this multiple quantum coherence to study this quantum information scrambling and see how this information is scrambling into the system. And now what we discover is that if we do this experiment where we compare the forward evolution with the perturbed evolution and we compare it with the ideal evolution, we have again out-of-time order correlation, but they are a bit more complex. So here you see, here is the ideal evolution and here the perturbed evolution. But what is more important is when we look at this cluster size of correlated spin, that is the effective number of correlated spins, now is an inner product between the scrambling of the ideal propagation of information with the how the information was propagated with the perturbed information. So this is the scrambling, the perturbed scrambling, and here is the ideal scrambling. And what I'm doing with the inner product is to compare how the information was scrambled by the ideal Hamiltonian and by the perturbed Hamiltonian. So this cluster size is actually showing how equal are actually this scrambling of information, so how equal is this information, how this information was propagated into the system, and is comparing these two things related with the number of spins that were correlated in the same way. So this is some kind of measure of how well the information was scrambled by comparing these two different evolution, that one have the perturbation and the other not. And this will tell you some kind of information about the scrambling coherent length of the evolution. So if they are equal, I can control the system coherently, but the perturbation is too large, we will see that this scrambling of information is too different, and we will not be able to have a reliable propagation of information. Okay, so now I will show you, this is more or less the tricks. I don't know if someone wants to ask some question about the concepts, and now I will show you the experiments.
So in the steady state, what do you expect the K? So in the limit of T infinite, what do you expect to see?
Well, I will show you now that with the experiments.
Oh, okay, great.
Okay. So now this is experiment is related with your question. This is the histograms that we do this partial density matrix tomography. They are the histograms, so this is the coherent orders of the density matrix. Here is the evolution time, and in the z-axis is the multiple quantum amplitude of the coherence of the density matrix. So at time 0, as I told you before, all the information in the density matrix is in the diagonal, so this is a very sharp distribution. Then I turn on the H0 Hamiltonian, the ideal Hamiltonian, and then what we see is that the information starts to propagate in the network. And eventually, there are no, because of thermalization, this information will be propagating indefinitely into the network. So this is the answer, I guess, to your question. If there are no, I mean, if the system behaves reasonably well, what happens is that this drop of thing will be propagated around all the network, and we see that actually in the experiment that this histogram, the width here in the inset, you can see the width of this histogram start to increase indefinitely as a function of time. So this information propagates freely into the network of SP.
Gonzalo, excuse me, a couple of questions. So one, so okay, you measure coherence orders until something like 120.
Yes.
So I'm trying to understand, what does it mean on the system size?
Yes, I will show you that in the next slide, but we were able to control the cluster size. The maximum number we attain is about 10,000 spins.
Okay, and second question, actually more on the theory part. So what is the difference or the connection with these Lieb-Robinson bounds? So at some point there was a Lieb-Robinson bounds which were more like, I think they were derived more for simple correlators, and now you have these autocs with more like 4 operators. Is there a fundamental difference, or in the end will it behave in a similar way?
Yeah, I mean, I don't know fully the details, but actually in the Lieb-Robinson bound, usually what you see is to see the correlation between two operators that have a distant, they are distant. So the out of time, the classical out of time order correlation are very similar. Also, you see how you see the correlation between two distant points, but I don't remember now. There are sometimes I was more familiarized with the Lieb-Robinson bound. I'm not sure that the correlation are exactly the same, but then you have to check into the paper. I don't have it completely in mind, but I think the Lieb-Robinson bound, the correlators that you use for the Lieb-Robinson bound, if I remember correctly, they are ordering time. So here is giving a bit of more information, but for sure they are correlated. So the propagation of information is bound by this Lieb-Robinson bound.
Okay.
People, what is trying to understand is when they are using this out of time order correlation to try to study when a system is chaotic. And what they saw is that this propagation of information propagates exponentially as a function of time. But this I'm not sure how correlate with the Lieb-Robinson bound.
Okay, thank
you. But for sure, I mean, the speed of that for sure is related with this Lieb-Robinson bound. So there is a bound of the propagation of information, and this is probably how fast this width of the distribution of the multiple quantum coherence can increase as a function of time.
Yeah. I imagine one point is to understand when you see something different between these two operator correlator of two operators and this autoc. Probably this is when you gain. If they behave a bit differently, maybe there is something extra. But okay.
Yes. So I'm sure that the what is extra is probably because you see this double commutator.
Yes.
This is giving you information about the degree of the scrambling of information, and in our case, is the number of spins that were correlated. So the Lieb-Robinson bound only tell you, I guess, no, I'm not completely expert on that, but tell you what was the distance of the propagation. But here is also telling you information about the number of spins. So I guess this is probably this is one of the main difference.
Mm-hmm.
But I'm not an expert on that. So if you want, then we can
yeah, and I don't think that for Lieb-Robinson bonds, I don't think people usually speak of information, only of correlations.
Correlation, yes. Mm-hmm. Yeah, but what I mean with information is that you want to see this the transfer. I mean, what you see is the transfer speed of information. So the people that are working in quantum channels, you want to transfer information from one place to the other, and the bound is the Lieb-Robinson bound. So people that is working in quantum channels, they use it to quantify the speed of transfer of information.
Okay, thank you.
Okay, so this is what happened when the control Hamiltonian is ideal. But now if I look at I do the experiment where I compare the perturbed evolution with the ideal evolution, what we'll see now when we look at the histogram of density matrix is that at time 0, they are very similar. But then we will see at the beginning, this is the width of the distribution. The black line is the ideal case. But then when we will see at the case that is perturbed evolution, at the beginning we will see that it's very similar to the ideal case. But then as a function of time, in some moment we will see that this distribution in the density matrix elements start to get localized. So this is what is giving us the information. Then this width is the number of spins that were correlated in a control wave, how well the scrambling of information are similar between the ideal and the perturbed evolution. And this is telling us that the scrambling of information in a control wave is localized. So I can propagate information, probably indefinitely with a perturbed and unperturbed evolution. But if I want to do it in a control wave, I can only assure that I can do it in a control wave for a bound of the number of spins that I can correlate. And this is the information that I'm getting from this experiment. So I see these localization effects on the fidelity of the scrambling of information into the system. So now putting it into numbers, as before there was a question. So now we extract the number of correlated spins as a function of time. Different colors are different perturbation strengths. So when the evolution is ideal, we can see that the cluster size increases indefinitely as a function of time. And in principle, there are no bounds. But if I have a perturbation, we can see that there are localization effects that they increase as a function of the perturbation. So one question, we started I don't know, I have how much time left?
So we started, I don't know, 50 minutes ago. 10, how long do you need?
No, I will try to do it in about 5 minutes, I guess.
I think 10-15 minutes is good.
No, I will try to do it faster. 5 minutes, I guess. So we see this localization effect as a function of the perturbation. Larger is the perturbation, the localization size is smaller. So that means that more perturbation, I will be able to control less spins. I will be able to propagate information in a control wave to less spin than if I have a very weak perturbation. Something very interesting that also we found, this experiment are started from a local information, but what happened now is the initial state is not local. So what we do is to use the ideal evolution to propagate information into the network and then use that as an initial state. So here the black line is the initial cluster size. I will consider that as an initial state. Then the different colors are different perturbation strengths. So as I showed you before, for a perturbation strength, I have a localization size. So here, for example, for the red, when the information is local, propagate until the localization size. But what we saw, it doesn't matter then if the information is local or is non-local, always the information, the scrambling size in a control wave will go to this localization size. So that means that the initial information is stored in a cluster size that is smaller than the cluster size. The information still will start to propagate in a control wave until the localization size. However, if the initial state is an information that is storing more spins in a cluster size that is larger than the localization size, the information will start to be lost until achieving the localization bound for the localization size. So this is some kind of dynamical equilibrium of the propagation of information in a controlled way. And something very interesting, that this is something that we did together with Robin Kaiser. Before we were working with Dieter Suter, and then we started to collaborate with Robin Kaiser, is that we found, if you see at this experiment, when the perturbation is very large, there are clear evidence that there are localization. But when the perturbation is very weak, it's not easy to see if there are localization or the dynamic is delocalized. Because at perturbation equal to 0, the information can propagate indefinitely as a function of time in a controlled way. So what we do is to use some kind of tricks from condensed matter physics and people working on many body localization or under localization to try to characterize these dynamics, and we use some tricks that are called the finite time scaling to try to extrapolate, try to predict if there are no localization for all the perturbation strength. And what we found is that there are a critical perturbation, that if the perturbation is larger than this critical perturbation, we see that the information is propagated, the information can be propagated in a controlled way, but there is a bound. There are a localization size where the information can be propagated in a controlled way. However, if we are able to reduce the perturbation below this critical threshold, we are able to see that we can correlate as many spins as we want in a controlled way. So this is very encouraging for quantum information processing, for quantum technologies, because this perturbation is not 0. So if we have a very weak perturbation, but it's finite, still we will be able to correlate as many spins as we want, because the propagation of information is delocalized. And the last thing that I want to tell you is that, okay, here I tell you that this is very promising. If the perturbation is weaker, I can control as many spins as possible. However, this is only the part of the dynamic that survived the perturbation, but the signal is decaying as a function of time. So I can correlate many spins, but the probability to correlate is very weak. So this is what I see if I look now at the fidelity when I compare the two evolutions. Here I'm showing you two plots, one with a very weak perturbation and one with a strong perturbation. So we will see in a weak perturbation, this is the blue line, we can see that the fidelity of the density matrix is decaying as a function of time. However, the cluster size is increasing indefinitely as a function of time. So I can correlate as many spins as I want, but the probability is much lower than if I do it a shorter time than in a larger time. So, and then this is the signal or the information that I will need to work on to process information. If the perturbation is very strong, we saw these localization effects, and what we found is when the perturbation is stronger, the fidelity decays faster, and when there are localization, what we found is that the decay of the signal now is exponential. So it decays exponentially with the rate that is constant. So here in the plot that I put below, what I did is the signal is a decaying function that is exponential with an argument. What we do is to look at the instantaneous decoherence rate. This is what I'm plotting here. This decay rate is the instantaneous decay rate. And what we see is that as a function of time, this decay rate increases as a function of time, but when there are localization, it saturates. So that means that this decay is exponential with a rate that is constant. However, in the regime that I don't have localization, this decay rate is lower, but increase as a function of time. And something that is, yes.
Excuse me, Gonzalo. It's not very intuitive to me why the fidelity decays faster when you are in a localized state as compared to a non-localized.
There are two things. Decay faster because the perturbation is stronger. So the information is lost more fast. However, when you see localization, the decay rate is constant. It doesn't grow anymore because the size doesn't grow anymore. So this is, I think, what you think intuitively. If there are localization, I don't see a reason why the decoherence should increase more, and this is actually what we see. It saturates. However, because the perturbation is stronger, the strength of the decay is larger, but because of the perturbation.
Okay. Okay. Okay, and then the size saturates.
Exactly.
Okay, thanks.
And this also, you can see it here. So here I'm plotting again the decay rate, but now instead as a function of time, as a function of the instantaneous number of correlated spins. So something that is very interesting that we found that the decay rate is proportional, is a power law of the instantaneous number of the cluster size of correlated spins. So that means that the decoherent effects are more sensitive, are stronger, as the number of correlated spin is larger, will decay faster the signal. So when I'm propagating information, as a function of time, I will have more spin, and the decoherent will start to decay. The decoherent will start to be stronger as a function of time, but this is determined by the power law of the cluster size of correlated spin. But something that is very important is that we have the power law exponent, that is alpha, and this power law exponent depends on the perturbation strength. And this is also related with your question. If the perturbation is very strong, the alpha is larger. So it's more sensitive, the system is more sensitive to the perturbation. When we have localization, this will grow the cluster size until there are a localization. When there are localization here, there will be accumulation of points. So the decay rate will be constant, but it's more sensitive to the perturbation because the alpha exponent is larger. But if the perturbation is weaker, we see that the slope of this power law, the exponent is weaker. And this is what I'm showing here. So here is two experiments with different perturbation interactions. Different colors are different perturbation strengths. So the darker colors are larger perturbation, and the lighter colors is a weaker perturbation. So this arrow is showing you how we decrease the perturbation. And we can see that the slope, this is a log-log scale, we can see that the slope start to decrease as a function of, by reducing the perturbation strength. So that means that the power law exponent decreases with decreasing the perturbation strength. And this is, in this plot below, I'm showing you the power law exponent as a function of the perturbation strength. And we can see that in the localization regime, we have a large exponent that is almost 1. So that means that the decoherent rate scale linearly with the number of correlated spins. However, if we are able to reduce the perturbation below a threshold, we can reduce, there is an abrupt reduction of the sensitivity to the perturbation extreme because this alpha exponent reduced to 0.5. So this is very important because if we reduce the perturbation in the localization dynamics, the method is we can connect as many spins as we want, but also the effect of decoherence are less effective than if we are in the localization regime. And then also what we do is to use these tricks that I told you before, from many-body localization, to use these finite time scaling techniques. And we saw that the transition between this scaling of decoherence is also consistent with the transition that I showed you before between a delocalization phase and a localization phase. And so this is also, so the method is very encouraging because if we are able to reduce the perturbation below a critical value, we can correlate as many spins as we want, but also the dynamic will be more robust against perturbation. So essentially, this was what I wanted to tell you. So I tried to show you how we can use techniques to monitor the quantum information propagation in a network, what is called quantum information scrambling. I'll tell you some tricks that they were developing in NMR, but now the people is starting to use it in several quantum systems because the techniques are general. I'll give you some tricks how we can measure the cluster size of correlated spin where the information was correlated. Then I tell you how we can connect this also with out-of-time order correlation and get information of the fidelity, how this information can be correlated in a control wave. And I show you how we can measure the number of spins that were correlated in a control wave by the ideal Hamiltonian. And I show you also that there are some bounds to the number of spins that we can control in a control wave. This creates a localization effects on the information propagation into the network in a control wave. Then also I show you these promising features that these localization effects only happen if the perturbation is larger than a critical value. But if we are able to reduce this critical perturbation below this critical value, we are able to correlate as many spins as we want. And also, as I showed you in the last slides, the sensitivity to a perturbation depend of the instantaneous number size of correlated spins, but the sensitivity of the perturbation that is related with this power law exponent is weaker if we are in the localization regime. So also we will have the decoherent effects are weaker if we are able to reduce the perturbation strength below this threshold. So with that, I want to thank our group in Bariloche. We started very, very recently a laboratory of nuclear magnetic resonance, and I want to thank in particular my collaborators, Dieter Suter and Robin Kaiser, and also the students that were involved, Cristina Rodriguez and Federico Dominguez. And we are working together also with Analia Suick. We are leading the lab together. So also thank to her. Thank you very much for your attention.
Thank you very much, Gonzalo, for the very nice presentation.
Thank you.
Are there some questions? More?
So I actually have a question regarding your perturbation Hamiltonian. So it's a particular perturbation Hamiltonian, right? But do you expect that these results can be generalized to? So what would be the characteristic of this perturbation Hamiltonian that gives you these results?
Yes, we didn't check that too much. We are checking now that. So what we did in this particular case, the perturbation commute with the initial state. Mm-hmm. So that means that the initial state is local, and this perturbation doesn't increase, in some sense, the number of correlated spins with the technique that we can measure. Mm-hmm. We use different perturbation, but both have the same concept. So it might be that because this perturbation commute with the initial state that produce this localization behavior. This might be a reason. Sorry. So what we want to check now is what happens if we put a perturbation that doesn't commute with this local state. Mm-hmm. Maybe this can change a bit the things, but I'm not sure.
Oh, I see.
This can change. I have to check it, no? But mm-hmm. What I'm sure is that this localization size, the concept is that I'm comparing two dynamics. I'm comparing, this is what I have here, I'm comparing two density matrix. Mm-hmm. So what I expect is that if I have a perturbation, always these two dynamics will be different. Mm-hmm. So if they are different, then this fidelity as a function of the coherent order will decay with the perturbation, and probably it will not be too important what is the interaction shape of the perturbation, because I expect that maybe we don't see localization, but for sure we will see is that the number of correlated spin will be reduced. Uh-huh. Mm-hmm. But the point that we have to check if there are localization or no localization, this is not too trivial to predict.
Okay, great. Thank you.
I actually had a related question on why this double spin exchange. If it's just you implemented this because this is what you had available, or do you expect it to have any special effect in going by delta m equal to 2?
I don't expect a special effect. So we do it actually because it's maybe also related with the previous question, that by using this Hamiltonian, that is the double quantum Hamiltonian, we are able to do this partial tomography of the density matrix. Of course, this also can be done with other Hamiltonian, but this is one of the more established and more robust techniques, the one that we use here. And the point is that this Hamiltonian also will create correlations, but with the technique that I measure, I will not see them. So this is also something very important because we are looking at the correlation, but that they are created by the H-naught Hamiltonian. So this also allows us to measure what was the correlation that survived the perturbation. So this is also another reason. But in principle, this technique can be done with other Hamiltonians. You only have to think a bit how to implement the experiments. But I don't know. I didn't do it, but I don't expect. I think the behavior is quite general. So the only thing is that might happen that maybe there are no localization. But I expect it's not too much dependent of the Hamiltonian. What I think is more important is that you need you need two Hamiltonian that compile and that produce dynamics in a different Hilbert space in some sense, or connect different type of space. And this competition is what I think generating localization effects. And at least we did some kind of phenomenological models that these phenomenological models are more related with the competition between two interactions than to the shape of the interaction. So this is the reason why I expect this will be a general result.
Okay, thank you.
Is there some study about quantum correlations like entanglement or quantum discord about in these systems? For example,
Yeah.
The first question is, can we measure some because if you have the state tomography, maybe we can compute experimentally the discord, even in case you don't have entanglement, but you can have discord, right? So maybe
yes, no, we did. I'm not aware if someone did it with this. Maybe yes, maybe there are some more older experiments done by NMR people that maybe they use that to measure discord. I think yes. But as I tell also before concerning, because this second paper here, they show how they use that to witness entanglement, and they do experiment with I think they were ion traps or some experiment with cold atoms that they witness entanglement, and they do this experiment to measure entanglement. So this is a paper that they do that, but not with discord, but with as a witness of entanglement. But in principle, probably I have to think a bit, but probably you can. I think there are some experiments with discord for older experiments.
Yeah, because for example, in a large system, maybe you don't have entanglement, but maybe we can use discord to explain some things or study
Yes.
the whole of quantum correlations beyond entanglement.
Entanglement, yeah.
Okay, thank you.
Thank you for your comment. Very nice.